Hello everyone, and welcome to the third video of the third lecture of the course on metric spaces. In the last two videos, we introduced two different distances on the sphere. So let me recall what we've done. We defined the sphere as the set of points P in the space R3 with x, y, and z coordinate such that xp squared plus yp squared plus zp squared is equal to 1. And then we've defined two distances on the sphere. The first distance, which we call d, between a point P of coordinates xp, yp, zp, and a point Q of coordinates xq, yq, zq, is given by the square root of xq minus xp squared plus yq minus yp squared plus zq minus zp squared. And this is the distance the sphere inherits from the space. The reason why we say this is that this formula here defines a distance on the space itself, and we are restricting it to the sphere to compute distances between points on the sphere. The second distance we defined on the sphere, which we denote d prime, is the one that associates to 2 points P and Q the length of the shortest arc on the great circle on which P and Q lie. Of course, if P and Q are antipodal points, there are many great circles on which these 2 points lie, but any of the great circles you choose will always give you the same result. So let me draw a picture to recall what this definition means. So we need the z-axis, the x-axis, and the y-axis. And we draw a sphere, which is the sphere of radius 1. Then we choose 2 points P and Q on this sphere, and we consider the great circle passing through these 2 points, which is the intersection of the sphere with the plane that goes through P, Q, and the origin. And this was the reason why we convinced ourselves that even if we were in a three-dimensional situation, we could go back to the plane I've just drawn in blue, and which is the plane through P, Q, and O, where O is the origin. And so we could go back to a two-dimensional situation. What we want to do now, as we have two distances on the sphere, is to compare these two distances. So first of all, we have to answer the question what it means to compare two distances. Well, a distance is a way to associate to 2 points a number, which is exactly the distance between those 2 points. So in our case, what we will want to do is we will want to find inequalities relating the distance between 2 points given by the two distances we have. Precisely, we want to prove that given P and Q in the sphere, then the distance computed using the first distance we defined between P and Q is always smaller or equal than the distance between P and Q defined using arc length, and the distance defined using arc length is always smaller or equal than 2 times the distance between P and Q using the distance inherited from R3. Proving two such inequalities will tell us that we can use either distance and we can obtain a bound on the other distance between the 2 points. How do we prove these inequalities? Well, proving the inequality on the left is easy enough in the following sense. We know that to compute the distance between P and Q using arc length, we have to take the maximal circle through P and Q. In particular, we can come back to the situation in which we're in the plane, and so we can draw the two axes, and then we have the circle on which P and Q lie, and I will draw them here, P and Q. And we know that if we draw the angular sector identified by P and Q, and we call alpha the angle identifying this angular sector, then the distance between P and Q is given exactly by alpha, given that we're measuring using radians. Whereas, if we were to compute the distance between P and Q using the metric inherited from R3, we would have to compute the length of the segment connecting P and Q in this way. However, we can see, and we know as well, that the length of the segment connecting P and Q, the yellow one, is smaller or equal than the length of the arc connecting P and Q. Therefore, this proves that the distance between P and Q computed using the metric inherited from R3 is always smaller or equal than the distance computed using arc length. To prove the other inequality, the one that says that the distance computed using arc length is more or equal than 2 times the distance computed using the metric inherited from R3, we have to work a little bit more. Recall that the length of the segment connecting P and Q in the picture we have here is given by 2 times the sine of alpha divided by 2. This follows if you consider the small triangle here on the left, and you use the theorem that relates the length of the hypotenuse, which in this case is just the radius of the circle, and it's equal to 1, and the angle we have here, which in this case is alpha divided by 2. Therefore, you get that the length of this segment here is exactly sine of alpha divided by 2, and then you have to multiply by 2 to get the length of the entire segment. Therefore, to prove the inequality we look for, we have to prove that alpha is always smaller or equal than 2 times sine of alpha divided by 2, which is 4 times sine of alpha divided by 2, but not for all alphas. We just need this for alpha bigger or equal than 0 and smaller or equal than pi. The reason why we need this just for these alphas is that the distance between P and Q is always computed taking the shortest arc connecting P and Q, which means that if alpha were bigger than pi, we were considering the wrong arc and we should have considered the other one, in which case alpha will be smaller than pi. So we have to prove this inequality, and notice that this is the same thing as saying that alpha divided by 2 is smaller or equal than 2 times sine of alpha divided by 2. Now, this inequality must hold for alpha bigger or equal than 0 and smaller or equal than pi. However, notice that if we input alpha equal 0, then we have 0 smaller or equal than 0, which is satisfied. And if we input alpha equal to pi, then we have pi divided by 2 smaller or equal than 2, which is satisfied as well. So we have to prove the inequality only for alpha bigger than 0 and smaller than pi, which means that we can divide by sine of alpha divided by 2, and the previous inequality is equivalent to prove that alpha divided by 2 multiplied by 1 over sine of alpha divided by 2 is smaller or equal than 2. And this must hold for alpha strictly bigger than 0 and strictly smaller than pi. Now, if we call t alpha divided by 2, then this is the same thing as saying that t divided by sen t is smaller or equal than 2 for t bigger than 0 and smaller than pi divided by 2. The only problem we could have with this quantity here is when t is equal to 0 or very near to 0. Why? Well, because we've got 0 on the numerator and 0 on the denominator, which means that a priori this quantity on the left might be very, very big. However, we proved that if t is very near to 0, then sine t divided by t is very near to 1. Which means that it is also true that if t is very near to 0, then t divided by sen t is very near to 1. Therefore, the quantity on the left is always a finite number for every t between 0 and pi divided by 2. In particular, we can prove that it is always bounded by 2. And this holds even if you input the boundary conditions, which are 0 and pi divided by 2, because we made the explicit computations above. How do we do this? Well, we consider the circle in the plane of radius 1, and we fix a point P here. Notice that this is what we're interested in because our angle has to be between 0 and pi divided by 2. Then we know that the y coordinate of P is exactly given by the sine of t, where t is the angle between the segment connecting the origin to P and the x-axis. Now draw the rectangle whose sides are the radius of the circle and sine of t. So it's this blue rectangle here. Then the area of this rectangle is exactly equal to sine of t, and this area is always bigger than the area of the angular sector whose angle is t, which means that sine of t is bigger or equal than the area of the angular sector. But the area of the angular sector, as we computed it in one of the previous videos, is equal to t divided by 2. Therefore, t is always smaller or equal than 2 sine t when t is between 0 and pi divided by 2. And in this case, we can also add the boundary conditions, because this reasoning holds whenever t is bigger or equal than 0 and smaller or equal than pi divided by 2, as you can see from the picture. Therefore, this proves the inequality we were looking at, alpha divided by 2 is more or equal than 2 times sine of alpha divided by 2, which in turn proves the inequality between the distance computed with arc length and the distance computed with the metric inherited from R3. This tells us that the two distances are not so far from each other, because we can bound any of them with the other. And this tells us that computing distances using one of them can give us information about the distance in the other metric. And this is all for the course. I hope you've enjoyed it. I definitely enjoyed teaching it. So before leaving you, I would like to give you an idea of where you go from here. So what can you do with metric spaces? Metric spaces are almost everywhere in mathematics because they're very easy to define, and they're at the beginning of other things and other concepts. For example, in mathematical analysis, you can use metric spaces to make sense of the concept of limit, which we basically used during the course when we said that the ratio of sine of alpha divided by alpha is very near to 1 when alpha is very near to 0. This is of course just one of the many examples of where metric spaces appear in mathematics. For example, functional analysis is another place where metric spaces are very important. Moreover, you could upgrade the definition and require more structure, not just a metric. You could define normed spaces or inner product spaces. Not only, you could also use metric spaces in geometry, defining topologies with them, and many other things. So they are definitely everywhere in mathematics, and they're definitely very useful. If you want, just look at the lecture notes and you will have some ideas of where to look for other places where they're useful. See you.